This is the lecture for the first half of section 2.2, Modeling Distributions of Data. In this lecture, we're going to talk a lot about a very special set of distributions called normal distributions. These are distributions of quantitative variables that have a particular shape and follow some very, very particular rules. And this particular distribution is going to show up so often in our work from here to the end of the year that we're going to spend a lot of time making sure that we have these ideas absolutely down. So let's dive in and talk about normal distributions. Um, Normal distributions have a particular shape. They are bell-shaped. They have uh, asymptotic behavior towards the axes. These ends just get closer and closer and closer to the horizontal axis. They are single-peaked. They are symmetric, which means that the mean and the median fall in the same place, which is dead center in the middle of the distribution. There's a particular spot on these curves um, where there's something called a change in concavity. And if you want to think about it, like right there, that's what they're saying there's a change in concavity. I want you to think about if you were a skier. There's a little ski guy going down the hill. There's this point where the hill stops getting more steep and starts getting less steep. That's where that change of concavity is. And that change in concavity is always one standard deviation above the mean. And so now seems strange, but we are going to talk about some new symbols here. We're going to use this symbol, which is the Greek letter mu, the lowercase Greek letter mu, spelled mu. And that's going to be our symbol for the mean of a standard, a mean of these normal distributions. We're going to use this other thing that looks kind of like a cursive O, but is really a lowercase sigma. Insert joke here. And that's going to be our symbol for the standard deviation. And it just so happens that for normal distributions, if you know the mean and you know the sigma, you end up knowing everything there is to know about that normal distribution because this is a density curve. And these density curves, again, are idealized ways of looking at the distribution of the variable. And these density curves actually are defined by an algebraic expression. We don't have to learn that expression, but there's an algebraic expression that draws these curves. All right? So normal distribution is described by a normal density curve. It is completely specified by two numbers, the mean mu and the standard deviation sigma. All right? It's symmetric. The change in curvature points are on each side and are exactly one standard deviation away from the mean. And we have a shorthand for describing a normal distribution with mean, mu, and standard deviation. And that is we use the letter uppercase N, parenthesis, and whatever the mean is, we put it in first and put a comma, and then the standard deviation in second. So that's our shorthand for writing a normal distribution with this mean and this standard deviation. Now, what's interesting, and again, we're going to like see these normal distributions like everywhere, and they just show up naturally in nature. For example, the heights of humans are normally distributed. So are blood pressures of humans. Blood pressures are normally distributed. Not everyone has the same blood pressure, but when you look at everyone's blood pressures together, they end up being naturally normally distributed. Birth weights are normally distributed. They just show up everywhere. And so it's really worth our time to learn a lot about them and get ready to apply what we learn in future problems. All right. So those of you who are taking AP Psychology, you may also learn about the 68, 95, 99, 7 rule. Now, this applies only to normal curves. And there are many different normal curves. The distribution of birth weights is very different than the distribution of blood pressures. But they all follow this rule. Okay, and here's the idea. If you go one standard deviation above the mean and one standard deviation below the mean, you will always capture in a normal distribution 68% of the data. We say approximately 68% of the observations fall within one standard deviation of the mean. If you go out two standard deviations from the mean, 1, 2, and 1, 2, you capture approximately 95% of the data. And if you go out three standard deviations, as you may guess, you capture almost all of the data, 99.7% of the data, almost all of the data. All right? So what does that mean for us? Well, let's say we have some data that's normally distributed. The Iowa Test of Basic Skills was given to seventh graders in Gary, Indiana, and it's close to normal. And we describe it as a normal distribution with a mean of 6.84. You can see it right there. And a standard deviation of 1.55, which means if you add 6.84 and 1.55, you get 9, no carry, 3 with a carry, and that's 8.39, and that's why that number's right there, because it's one standard deviation above the mean. And there's two standard deviations of mean, three standard deviations above the mean, one standard deviation below the mean, two standard deviations below the mean, three standard deviations below the mean. So we can ask questions of this distribution, like what percent of the scores are less than 3.74, which is right here. In other words, hey, how much area is in this little tail? Now, the 68, 95, 97 rule doesn't tell us that information um, uh, with one of those three numbers, but it does allow us to say, you know what, hey, here I am, and this number is two standard deviations below the mean. I can also go two standard deviations above the mean, and here in this middle is 95% of the data. Where's the other 5%? Well, because of the symmetry, that 5% is equally broken up in the two tails. Half of the 5% is in one tail, and half of the 5% is on the other tail. And in using that little fact, we can see that about approximately 2.5% of ITBS scores are below 3.74. And I put in the ITBS scores because that statement provides context, and I want every one of our answers to have context in them. Okay, that was so much fun. Let's do it again. I'm going to erase what I put in here. And then the second one, we're going to say, well, what percent are between 529 and 944? Okay, well, we already know a couple of things, like this area here, because of the earlier work, is 2.5%. We also know that between these two lines, we have 68%. Let's see if we can pull all these things together. Okay, let's break this down into two pieces. On this side, on the blue side, I've got half the data, but without that 2.5%. So on the blue side, on the right side, I have 50% minus 2.5%, which is 47.5%. Okay, now let's go over to the green side. On the green side, I got this part. Well, wait, that's all of this area is 68%, and this is half of that area. So on the green side, I think I got half of 68, which is 34%. Now, if I want to know how much is between here and there, I can add those two numbers up. 34% plus the 47.5%, that's a 5. Uh, 7 plus 4 is 11, carry the 1, 80. Looks like about 81.5%. And then let's write our answer out. About, not exactly, because these are approximates, about 81.5% of, let's add context, ITBS scores. Gosh, I need a thinner marker. Let's try this. That's the thicker marker. There we go. Scores are between, what is it, 5.29 and 9.94. And I'm modeling, again, the way I want the answers on our quizzes and tests, including context. All right. So moving on, there's one very special normal distribution. Again, there's many normal distributions, but there's one special, and it's called the standard normal distribution. And it's a normal distribution, single peaked, bell-shaped, standard deviation at these changing curvatures. But the standard normal has a mean of 0, so it's normal with a mean of 0 and a standard deviation of 1. Okay, I'm sorry, I wrote that in the wrong spot. Let's try that again. The normal distribution is normal, 0, 1. And remember our z-score, because this is also called a z-distribution, is x minus mu over sigma. Now, you may recall that this is a transformation. This transformation, if I put something that's exactly the mean right here, I get mean minus mean, I get 0. That gives me a transformed mean of 0. And if I put something that's exactly one standard deviation above the mean, I end up getting a value of exactly 1. If I put something that's one standard deviation above the mean into this formula, these cancel. I get sigma over sigma, I get 1. So the transformation of anything into a z value creates, sorry, the transformation of any normal distribution into z values creates a standard normal distribution. Now, the reason why this is so very special is because we can use the standard normal distribution to do calculations of how much proportion of some event falls in a particular range. With the 68, 95, 99, 7 rule, we can do it if everything lies nicely on those one standard deviation above the mean, two standard deviations above the means. But we've got an additional tool that will allow us to handle almost any different standard normal calculation. All right. And the way we do that is to use something called a standard normal table. So a standard normal table in our book is called Table A. All right. And it shows the areas under a standard normal curve, and it gives numbers that are under the curve and to the left of the z value. All right. So for example, if we look up the value 0.81 on a standard normal table, it says if I go to z equals 0.81, draw a line, go to the left, and stay underneath the curve, that area under the curve, oh, I'm sorry, that's not where 0.81 is. This is where 0 is. This is where 1 is. 0.81 is actually about here. 0.81. right? And we say if we shade in that area to the left of that line and stay underneath the curve, it represents about 79% of the entire area under the curve. All right? So we're going to be using the standard normal table to find these numbers. All right? Let's see this in action. As I said before, um, okay, if we look for 0.81, well, we find the zero point 0.8 in the left-hand column of our table A, and then we look for the 1 as one of the headings across the top. So this provides the units and the tens digit, and this provides the hundredths digit. And that area is 0.7910. Now, this is only a small portion of a standard normal table. And this kind of problem where we just look and find the answer in the table, we're going to call that the easy problem. And it's easy because we're going to the left, because we're finding the value that's less than. Having a less than is the thing that makes this easy. But what I want to show you is like, this is only part of a table. Here's what it looks like when we have the entire table. Okay, here's the entire table. All right. And with the entire table, let me just lock this down so when we write over the top of it, it doesn't want to do that, does it? One more time. Nope. All right. So when we look at the entire table, we have to find the 0.08. Here's our 0.08, and here's the 0.01, and there's that 0.791 getting read off the table. Okay. Again, those problems are the easy problems. Now, when we have different problems, okay, so it says like finding the area to the right, we're going to have to do a little bit more work. When this is a greater than symbol, z is greater than, then we call these the 1 minus problems, right? 1 minus problems. Why is that? Because the table will read off the area to the left. This says that we want negative 1.78, but we want the z-scores that are greater than that. Well, because the total area under the curve is 1, we can look up the number to the left and subtract it from 1. And when I subtract 1 by 0.375, I get 5,269. Okay, 9625. All right. And does that look like about 96% of the area under the curve? That's a lot of area under the curve. So the answer is yes, that answer looks appropriate. Which reminds me, um, when we do these problems, always draw the normal curve, right? And shade for your answer. That way, if we forget to do the 1 minus, it'll show up. If I left my answer as just 3%, does this look like 3%? Not at all. Not at all. So always draw your normal curve and shade. Um, let's go ahead and let's take a look at the last version. And the last version is the one that I call high minus low. Okay, in high minus low, we are interested in being between two z values, right? Like being between positive 8.1 and negative 1.25. Now, the way we do this is we'll find all of the area for the larger value, and then we'll subtract off the little area that we don't want. So the probability or the proportion of z values that are between negative 125 and 0.81 are, Well, we look up the value for 0.81. And again, that value, according to the Z table, was 0.7910. And then we're going to subtract it from the value that we get from looking up negative 1.25. So let me go back to table A. Let's erase that. Back to table A, negative 125. All right. So here's my negative 1.2, and here's my 5. Let's see where they intersect. Right there. 0.1056. 0.1056. And if we subtract these two, which I did when I was preparing this lecture, we get 0.6854. And that's how we do the three different versions. Remember the three different versions. Easy is when we're less than. 1 minus is when Z is greater than. And then again, high minus low when we're stuck between two Z values. So I'm going to skip over that part. Let's just see if we can get these values uh, off of our tables. I'm going to demonstrate again the kind of work that I want to see from you. We're going to draw a normal distribution. There's a 0, there's a 1, there's a 2, negative 1, negative 2. That's a standard normal distribution. 1.39, that's about here. And I want to be less than. So I'm looking for this area below that 1.39. This is a easy problem in that I am simply going to write the answer found in table A. Let's go look up 1.39 in table A. Okay, let me get rid of my old drawings. 1.39. So look at 1.3, and then 9 is all the way over to here. So that number looks like it is 0.9177. 0.9177. And then we ask, does that look like it's about 91%, 92% of the area? Does to me. So I'm feeling pretty good about that. Okay, next problem. Again, draw that normal distribution. Middle at 0, 1, 2, negative 1, negative 2. And again, about that changing curvature for the place for the 1. Negative 2 is way down here. Oh, but we want to be greater than that. Okay, that means this problem is a 1 minus problem, right? So the probability that Z is greater than negative 2.15 is going to be 1 minus, and then I'm going to look up negative 2.15 on table A. All right, negative 2.15. Okay, negative. So here I'm in the negatives, negative 2.15. So it looks like that number is 0.0158. 0.0158. And if I subtract those two, say I get a 2, a 4, an 8, and a 9. All right, so does this look indeed like it's about 98% of the curve? Does to me. All right, let's do one more. Again, you'll get practice, you'll get better at drawing the normal distributions. 0 is our change in curvature about 1. Same distance to get to 2. Negative 1, negative 2. Negative 0.56, which is about here. and negative and positive 1.81, which is about here. And that's the area that we want. This is a high minus low problem. So the probability that we're between negative 0.56 and 1.81. Okay, we'll start by looking up 1.81 on table A. 1.81, which we need to be the positives. 1.81, 0.9649. 9649. 0.9649 minus, and now we'll look up that negative 0.56 in table A. All right, negative, okay, this is going to be tricky because I get the negative 5 and I have to get that top row in there. Negative 0.5, and then over to the sixth column is right there. So 0.2877. 0.2877. And if I subtract these two, and I did that on a calculator earlier, I get 0.6772. And then we look back and do we think that looks like about 68% of the curve? And the answer is, I think it does. So we're good. Now, the last version of the using the table that we have to do is called the working backward problem. Working backward. Now, in all the other problems, we were handed a z or two z values, and we looked up a proportion or a percentage. In this version, we are given a percentage, we're given a proportion, and we're asked to look up a z value, right? So I want you to imagine we have our standard normal distribution again, and I want you to imagine that we're looking for the 20th percentile. Now, 20th percentile. I kind of know that here's where the 2.5 percentile is because we did that calculation earlier. Um, if you do a little of extra math, 100 minus 68, because the middle is 68%, gives you 32. And then 32, half of that is actually, this is like the 16th percentile. The 20th percentile is like somewhere right in here. And that's, again, the line with 20% below it. Now, how are we going to do that using table A? Well, we're going to go to table A, and instead of taking the z value and trying to find the number in the middle, we're going to start with a number in the middle and then find the z value. So we're going to look at the vast middle of this table and say, where's the number that's closest to 20%? And I think that number is like right about here. There's 0.2005. Now 0.1977, that's close to 20%. It's about 0.0023 off. This one's about 0.0005 off. So this one's closest. So we're going to say that's our number. Now what's the z value associated with that? Go over to here, negative 0.8, and then go up to the top, and our hundreds digit is 4. So we can say that negative 0.84 is at the 20th percentile. And that number fits pretty well with what we thought it would be when we drew that out. Let's try this again. Draw the distribution, 0, 1, 2, negative 1, negative 2. We want a value of z where 45% of all the observations are above it. Well, 50 is right at 0, so 45 is like right in here, I think. Okay? And there's the 45% that's above it. Okay, now here's something tricky. The table only works with the, I can't select that, right? With the area below it. Remember, the table says this is how much is below or to the left of that z value. If 45% is here, 55% is there. And that's the number that we're going to have to look up in the middle of the table. So let's switch one more time over to the table. Okay, let me erase my old work. And I'm looking in the vast middle of the table for 55%, or the number that's closest to it. Well, here are the two numbers that are closest to 55%. And this one is 17 thousandths too big. This one is 22 thousandths too small. This one's the closer of the two. So we're going to say 0.13 is our answer. That z equals 0.13 has 45% of observations above it. All right. And that is going to conclude this first half of the lecture for 2.2.